So we describe Ohm's law. So Ohm's law writes a relationship between current density and electric field applied to the cable. Actually, not cable. Any substance, any medium, if you apply the electric fields and if it's conductor, so you can drive electron. It doesn't matter it's a cable, cylindrical cable, or it can be a substance. So I apply the electric field. So it doesn't matter if it's in the cylindrical shape. So current density, as you see, directly proportional to the electric fields. If the behavior of current density as a function of electric field gives a straight line, this is the ohmic behavior. So ohmic behavior means that current conductivity of the material doesn't change. Constant. Conductivity is constant. Sigma is constant. But a non-ohmic behavior, as you see in that curve, current density not directly proportional. It's proportional to electric field, but there's a non-linear behavior. Sometimes with the electric field, current is decreasing, sometimes increasing. So not always increasing by the electric field. So different cases. So why, for example, here, why electric fields, when I increase the electric field, current is decreasing? Because this cable or this media substance store electron inside with the electric. Okay? But there are some interesting mechanisms in that system. So this is non-ohmic behavior. We call if particles, if the substance has a constant conductivity, this is ohmic behavior and ohmic material. But if the conductivity depends on the electric field and changing by electric field, this is non-ohmic behavior. Then we write also define the resistance, and we measure with resistance how the material acts against the current. So when we drive the current, because of collisions between electron and atom, each substance experiences some resistance to the moving electron. So electrons are free, but they are not moving in this free space. They are moving in some media. So in this media, there are too many electrons with atom try to move. So they hit atom. Also, one electron repel another electron. Imagine that more than 3 million electrons in the same volume try to move. So because of that reason, electrons' acceleration always low and about 0, and we assign also drift velocity, very low speed. They are moving with very low speed. This reason actually comes from rho. So rho is the resistivity. Resistivity shows these collisions between electrons. So if the electrons collision is number of collision is high, we have high resistivity. Another factor, length. So cable's length, of course, important. So if you drive electron in a long way, so you will increase the number of collisions. Why? Resistance inversely proportional to the thickness, because thick cable, more free space means. So electron can easily move in thick cable, but cannot easily move in thin cable. Thin cable, small volume, that means no free space to move for electron. Free, okay. So rho is resistivity inverse of conductivity. Conductivity shows that if the material like silver, copper, gold, these are conductors, they have high conductivity, but like silicon, diamond, plastic, PVC, for example, water, pure water, these are good insulators and their resistivity is high, conductivity is low. Okay, so these are 3 important relations. Ohm's law, we can write Ohm's law in that two different form. Delta V over I gives the resistance. This is the Ohm's law. Another form of Ohm's law, current density and electric field relation, and resistance given as a function of rho. Rho is the resistivity of the cable. Then we describe also rho as a function of relaxation time, also current as a function of relaxation time. So relaxation time actually comes from that collision of electron. So electrons are colliding when we apply the electric field, as we explained before. In this case, acceleration of the electron is about zero because electron continuously collide with another electron. For example, that number for copper is 1 trillion times in 1 second. In 1 second, copper electron hits another copper electron 1 trillion times in 1 second. 1 trillion. Imagine 1 second, you have a car, you are colliding with another car 1 trillion times in 1 second. So it's impossible to move. Right? So it's impossible to move. That's the case. Electron hits another electron, come to rest. Relaxation. Accelerates because of collision, decelerate. Come to rest. Relaxation. This is the relaxation. Also, you can imagine the relaxation time for the car in traffic. Car at rest. In motion at rest. In motion at rest. This is the relaxation of the car. Of course, there's no collision, but it will stop finally. So it's because another car will stop and it cannot go. There are too many cars around. It's not easy to move. This is the relaxation car. Relaxation times for the car life electron. Okay. So because of this high number of relaxation, small time, this short relaxation, because of the short relaxation time, electron speed is very low because relaxation depends on the acceleration and the velocity depends on the acceleration and relaxation time. Let me give one example. Let's say we apply here. So what is the equation? Drift velocity, acceleration, and relaxation time we multiply. So QE over M is my acceleration time. QE over M, my acceleration. Let's apply 1 Newton per coulomb. 1 Newton per coulomb electric field. For example, what is 1 Newton per coulomb? 1 Newton per coulomb. If I apply the cable 1 volt on the and length 1 meter. 1 volt, 1 meter length. 1 Newton per coulomb. It's very simple. I can apply. 1 volt, a small battery can supply the 1 volt. No problem. 1 Newton per coulomb is not a strong electric. Okay, 1 Newton per coulomb. What is the mass of the electron? This is the mass of electron. What is the charge of electron? Charge of electron, 161090, you know, coulomb. So if I calculate its acceleration under 1 Newton per coulomb electric field, what is acceleration? What is acceleration? QE over M. So 16 over 9. Here minus 19. But this will be plus 31. What is acceleration? 1.6 over 9. All 17. So acceleration is 0.17 times 10, 31 minus 19. So it gives 22, right? Plus 22. Or 12. Which one? 12, sorry. 12. As you see, huge acceleration. So if you remove this 0, this 0, so 17 times 2 times, that means it's about 1 trillion meters per second square. Acceleration is huge. Under this acceleration, electrons should fly in free space, but maybe at the speed of light, according to this acceleration. But problem is collision. Yes, acceleration is huge, but there is no free space to accelerate electron because another electron hits the electron, drift velocity. This is all 17, 10 plus 12 times 10 minus 13. This is top. So speed break because of power. So this is minus 1, that is 0.017 meters per second is the drift velocity. Okay. So finally, drift velocity is 0.017 meters per second. That explains, yes, we have huge acceleration. Acceleration is huge, no problem. Because electron is small, 1 meters per coulomb field is enough to give a huge acceleration. But problem is not acceleration. Problem is relaxation time. Problem is resistance. Problem is electron collision. Let's remove all electron, drive only one electron. Is it possible? To remove this, decrease the relaxation time, this is the solution. Let's accelerate not 3 electron in the cable. 10 electron is enough. Is it enough? What happens if I drive, for example, 100 electrons? In my cable, there are more than 3 electrons. That causes relaxation, collision. So relaxation time is very short. Let's remove electron, remove them. 10 electron is enough, or 100 electron is enough. If I say, what happens? What is the problem? I decrease the number of electrons to increase the current. Can I increase the current? For example, what if I drive 10 electrons? How many electrons in 1 ampere currents? 3 about. We calculate here. It's about how many electrons I give maybe in the previous week's lecture. How many electrons? Yes. How many electrons? Here, 6 times 10, 18 electrons. This is 1 ampere. But if I drive here 10 electron or 100 electron, current is nanoampere or picoampere. So this energy is not enough to run it. That's the problem. So we need too many electrons because they carry some energy. Each electron carries maybe picojoule or nanojoule. I need really 3 electrons to get enough energy to run in the device. That's the problem. Yes, decreasing number of electrons is a solution for relaxation time. In this case, because not enough electron, we cannot run this. You can drive the current, no problem. But energy carried by electron is not enough to run a lamp or this projector or diode. Okay, that's the problem. Each electron's energy is very small amount energy carried by it. So that's the reason why we have more than 3 electrons removing in the table. Okay, so after this, we start resistor. So resistor, as you see, is a circuit element. We use resistor to tune the current. And we described, as you remember, also in capacitor chapter, previous chapter capacitor, we have 2 kinds of combination, series combination and parallel combination. And I gave this homework. Let's solve this homework first. Then today we will continue. Other topic is electric energy and power. So we concentrate energy of the system. Okay, let's solve the homework. So homework says that current on this resistor is 1 ampere. Actually, I forget to give you direction of the current. This is important in that question. So I should give you in which direction current flows. So I forget it. Now I will add the direction of the current. So this is the direction. Current flows from C to other, so come from the C. Other part we can label, for example, we can say D. So this is the rightward direction. We have current is 1. In this case, what is potential difference between 2 points, A and B? Let's calculate potential difference first here on resistor curve. I will mark this point as D. This is B. This is also C. Same potential. This is C. This is D. So as you see, this is the free cable. This potential is the same as this potential. Also, this potential are same D. But this potential, because we pass through the resistor, will be different. Let's say this is E. This is E. This is E. So if I mark each point having different potential, it's easy to analyze the circuit. This, if it's A, this is the same A, because this is the free line. This is A, this is A. Yes, as you see, how many different potential? A is a potential, B is another potential, C, D, 5 different potential. I can read 5 different potential in my circuit. Now, VC minus VD, because here current flows from C to D. Let's show. This is the second resistor. This is point C. This is point D. This is the direction of the current. This is very important case. If the current flows from C to D, that means potential of C is bigger than potential of D. Why? Because current always flows from high potential to the low potential. So potential at C, I can read with my voltmeter, bigger than D. So VC minus VD is a positive number. VC minus VD, potential difference, this is delta V, from Ohm's law by R. R2. So what is the current? 1 ampere. What is the resistance? 12. This is 12 volts. 12 volt potential difference. I know potential at C is 3 volts. What is the potential of D? If this is 3 volts, given in the question, I can say, what is the potential of D? What is the potential? Minus VD equal 12 minus 3, 9. VD is minus 9. Okay? I calculate first potential of D, minus 9 volts. Now, 3 minus 9, 12. Okay? Left side positive, right side negative potential. So D is negative, minus 9. Now, I understand this is 12 volts, 12 volts. This is also 12 volts because R3, R2 parallel line. So I am writing VC minus VD from here, from this branch. VC minus VD also. Gidelim şöyle bir saniye. Tarafa gidelim. VC minus VD also can be written as a function of R3. Let's say this is the current I. This is current on R3 times R2. So what is the, why I'm writing VC minus VD from the other R, other branch? Because I want to calculate current on R3. So this is my question. What is that? So VC minus VD, 12, we have already calculated 12. This is 4. What is the current of R3? What is the current? 3 ampere. So Current on R2 and R3 is known. I can calculate what is the current on this branch. So let's say, what is the current here? Maybe I can say this is I prime. This current is I prime. This current I double prime. So this is I prime. What is I double prime? Summation of two currents, because it's splitting. Current I double prime comes, then split. So I double prime, I plus I prime. So I double prime is 3 ampere plus 1 ampere, 4 ampere. So this current is 4 ampere. This is also same 4 ampere, I double. Okay? Sorry, not. This one, I double prime. This is another current here. Okay, so we should find first what is the current here? 9 ohm. Current on 9 ohm is another question. Now, I understand I double prime is the 4 ampere. Now, I can calculate AE potential difference. This part. Potential difference between point A and point E. This is completely this part. So parallel to this one. This is also AE. As you see, this is AE. So I know this current. Sorry, AD. Yes. We will calculate this AD, this is AD, then AE, AD, and last step. Let's find AD. What is AD? VA minus VD. VA minus VD. So VA minus VD, I can write VA minus VD equal. What is VA minus VD? I know this current. If I write here the total resistance, I can calculate. So current flows through this total resistance. What is the total resistance? I double prime times R1, 2, 3. Their combination. Okay, three resistor times the current I double prime. In this case, I double prime 4 ampere. 4 ampere. What is R1, 2, 3? These are in parallel combination, series to R1. What is the total resistance? Let's find first R2 and 3. 1 over R2, 3 equal 1 over R2 plus 1 over R3. Here, R2, 3 gives 48 over 16. It's 3, right? 3 ohm. Totally 1, 2, 3 gives 9 ohm. This is 9. So 36. VA minus VD is 36 volts. Then this is 36 volts also, because these are parallel arms. 36. What is this current? Current on 9 ohm. So if this is also 36, I can write current of 9 ohm. Current of 9 ohm, 36 volt over 9. What is the current? 4 ampere. Okay, so I calculate also this current of 9 ohm. This is the current of 9 ohm is 4 ampere. What is the current here? 4.5 ohm. What is this current? Let's say I star. I star. Let's put another notation, I star. What is I star? Yes, 4 comes from this line, from the other line, I double. So this is the summation of these two currents. Current of 9 ohm plus I double prime. This is I star. So I star is the current I star, the current of 9 ohm plus I double prime. 4 ampere plus negative 4 ampere, 8. I star is 8 ampere, this one, 8 D. So if This is 8 ampere. What is the potential difference? VD minus VE. I can calculate potential difference VD minus VE. Then VD minus VE is given by I star times 4.5 ohm. So I star is 8 ampere. 4.5. It gives 36. Yes, 36 volts. Okay, what is AE? This potential difference, AE. VA minus V. This is VA minus VD plus VD minus V. Summation of two potentials. VA minus VD we have already calculated. This is VA minus VD 36 volts. And VA this one 36 volts. We have already calculated before 36. This is also 36. Totally 72 volts. A minus V. Last step. What is the last step? EB, potential difference EB. So I calculate I star, current I star. So I should calculate also potential difference. I should calculate total current. I total pass through the 1 ohm and 1 ohm resistor. Let's say I double star. I double star is my total current. So I know this is I star. Another current comes from here. Summation of two current I double star. What is this potential difference? AE I know. Where is it? VA minus VE. And 72 volt. I know this is 72 volt. This is 9. I know the current. What is the current? On 9 ohms. But there are two 9. Let's assign another current. Let's say I 3 star. This is I 3 star current. So I 3 star is 72 over 9. I 3 star 72 volt over 9 ohm, 8 amp. Then total current I double star. I 3 star plus I star. This one 8, this one 8, 16 ampere. And finally, if the current here 16 amperes, 16 volt is the potential difference. VE minus VB is 16 volts times 1, 16 volt. What is VA minus VB? VA minus VE plus VE minus VB. So this two cancel and it gives 72 plus 16, totally 8 volts. This is the total potential difference between two groups. Okay, so step by step, I also analyze full circuit. I calculate all currents in my circuit. I calculate all potential difference in my circuit. This is the full analysis of the system. So any current you can calculate or any voltage in any point you can calculate using this equations. That solution, using the solution. For example, if I ask you, what is potential A? What is VA? What is VA? I know VA minus VC. Where is VA minus VC? We know C and we know VD. Sorry, VD. We know VC is 3 volts. Yes. C is 3 volts given in the question. VA minus VC. VA minus VC is what is VA minus VC? Where is it? We didn't calculate, but we know VA minus VC, I double prime times 6 ohm. What is I double prime? 4 ampere, 24 volts. In this case, what is VA? 24 plus VC. What is VC? 3 volts, 27 volts. I know what is VA. What is VB? Let's find VB. But first, we should know what is VE. We know VD, as you see, VD minus 9. Here, VD is minus 9. VD minus VE. VD minus VE is, where is VD minus VE? 36 volts. 36. I know VD is minus 9. What is VE? What is VE? If I transfer VE right side, 36 left side, minus 45. This is VE. Now, let's check. Okay, we haven't finished. VE is minus 45. Okay. Then VB. What is VB? VE minus VB equal 1 VE minus VB 16 volt. I calculate here 16 volts. E is minus 45. What is VB? What is VB? Minus 45 minus 16. 71. Minus 71 volts, right? Yes. 71. Doğru mu? 61, sorry. Değil mi? 61. Let's test now. VA minus VB again. This is 27. This is minus 61. What is top difference? 88. Same. I can test. Okay. So you can find all of potential. I know A, I know B, I know C, D, E. All of them. All of them I can find. Yes. Yes, this is the homework. Now today, actually, that was a review of last lecture. Today's lecture is electric energy and electric power. Electrical energy and power. So what is the energy carried by electron? You know, we run all devices with electric current. So when we drive the current, I can get the light from the lamp. I can get the light from the projector. I can get some light and not maybe sound from my screen, laptop. I can communicate with my phone, connect to internet, but I have to drive the current in my circuits. Electronic devices works with electric current. But electric current is not enough to run the system, because if the electric current carries low energy, not enough to run my projector, my laptop, or another device. For example, this projector works with some electric current, yes, but also under some potential. So not only currents, but also potential difference you apply to system is very important. For example, maybe this projector works with 1 ampere current. My phone, when I charge my battery, I am driving 1 ampere current. The energy consumed by this projector is not same as my battery, right? This needs a high energy because it runs this lamp and its power is very high. As you see, it's illuminate, shine that huge screen. but my phone only shines this small screen. So currents can be same. Current is same, but energy carried by current is not same. 1 ampere current in my phone, 1 ampere current in that projector, they carry different energy. So energy becomes important when I transfer the energy and when I run a system. Energy is much more important than what is the current driven in the system. Now we will calculate energy carried by the electron. Let's take a cable again. So electrons are moving and each electron carries some energy. So let's remember energy potential relation. We explained in previous chapters. We describe electric potential energy between two charges, Q1 and Q2 are. What is the energy of Q1, Q2 charge system? K, Q1, Q2 over R. This is the energy. If the two charges are close to each other, energy is high. If the distance between the charges is getting bigger, energy is decreasing. For example, if I double the distance, even if I have the same amount of charge, I don't have the same energy. So in energy, distance between the charge is very, very important. Also, when you transfer electron, that distance between the electron is bigger, is getting bigger, energy of electron is decreasing because of that reason. Okay? So if you transfer electron and keep the distance between electron is very small, you transfer high energy electron. High energy electron. So energy depends on the distance between the electron. Why distance? Because this is the electron, repulse energy electron. But you keep them together. So that means they carry high energy because they repel each other. With that repulsive force, they can do something. So low energy, for example, this is the case. This is the cable resistor. What is this resistor? For example, there's a lamp here. Lamp. Lamp. Light bulb. Lamp gives the light. So why lamp gives the light? Where this energy comes from? Electron coming to the lamp. These are electrons coming to the lamp. These are electrons coming to the lamp. This one. İnceldi. Yani ben burada kalın şey. Neyse. Okay, these are electrons coming to the lamp. They have high energy. For example, these are distance between the electrons. They are moving, coming in. After they pass through the lamp, they give their energy to the lamp. And lamp gives the light, you know. After this energy transfer, same. How many, for example? Let's say that 6 electron, 1 second is coming. Not 6, maybe 6 but let's show 6 electron. 6 electron per second coming in. After they release their energy, what is the case? This is the electron's distance. Now they have that distance after they release their energy. Okay? After the electron gives their energy to the lamp, they leave this cable, this lamp, with high distance. There is nothing change in number of electrons. Say, how many electrons coming? Same electron coming. What is the difference? Before they come into the lamp, they are close to each other, high energy. After they release their energy, distance is increased. But same number of same number of electrons is moving. So there is no loss in currents. There is no loss in charge. Where is the loss? Loss in energy. What does it mean energy? Distance. Okay? Distance. So this is the energy. So how the system works. If the energy between the charges is this one, I can write also U as a function of V. What is V? Potential of Q1 times charge Q2. So I can write this energy in this form. Potential of Q1 times Q2 or potential of Q2 times Q1. This is also possible to write. So there's the relationship. U is 2 times V. So there are two charges. One is the source, the other is test. I'm taking one of the charge times the other charge potential. Now, in that system, what is the energy of electron? What is the energy of electron? I can write here how many electrons we have. I don't know, trillion, more than trillion. Instead of Q, I can write here. I can write here current. So instead of Q, I will write current. What is the current? Delta Q over delta T, right? This is the charge passing through the cable. What is the Q? I delta T. Then if I substitute this into the equation, I can define energy of the moving electron. What is the energy? If I substitute Q is I delta T, this is delta V times I times delta T. Here is the energy carried by electron in the cable. You know, this is the volt in volts. This is in ampere. This is in seconds. Volt, ampere, seconds. It's joule. Energy carried by electron in the cable as a function of current. I'm not writing as a function of charge. I'm writing as a function of currents. As a function of currents. Applied potential difference applied to the system times the current times the time. So, and in case of energy, we need to say what is the time interval. How much second, how much minute we apply the current. This is the total energy carried by electron. Okay, one example. Oh, not there is no time for example. After break time.